the backbone of railways understanding track alignment. Railway track alignment is the foundation upon which the entire rail system operates. It's much more than just laying down tracks, it's a complex engineering feat. Track alignment encompasses the horizontal and vertical positioning of the rails. This includes straight sections, curves, and the transitions between them. A well-designed alignment ensures smooth and safe train movement. Horizontal alignment focuses on the track's layout as seen from above. Think of it as a bird's-eye view, revealing curves and straight sections. Vertical alignment, on the other hand, deals with the track's elevation changes. This includes slopes and vertical curves, crucial for managing uphill and downhill sections. Proper track alignment is essential for the safety and efficiency of railway operations. It minimizes wear and tear on both the tracks and train wheels. A well-aligned track also ensures passenger comfort by reducing vibrations and jolts during the journey. Precision is key measurements and train speeds. Accurate measurements are the lifeblood of railway track alignment. Surveyors use sophisticated instruments to ensure every inch of the track conforms to the design specifications. These measurements determine the track's horizontal and vertical position. They also dictate the degree of curvature on bends and the transitions between different sections. The precision of these measurements directly impacts train speeds. On straight sections, trains can achieve higher speeds due to the minimal resistance. However, curves require a reduction in speed to prevent derailment. The sharper the curve, the slower the train needs to travel. The relationship between track alignment and train speed is critical for safety. Engineers carefully calculate the maximum safe speed for each section of track based on its alignment. These speed limits are strictly enforced to prevent accidents and ensure smooth operation. Mind the gap track gauge and international variations. Track gauge, often referred to as track width, is another fundamental aspect of railway track alignment. It refers to the distance between the inner edges of the two rails that make up the track. This seemingly simple measurement has significant implications for train compatibility and international rail travel. Different countries and regions have adopted varying track gauges over the years. The most common track gauge worldwide is standard gauge, measuring 1,435 millimeters or 4 feet 8.5 inches. However, broader gauges, like the Russian gauge, and narrower gauges, such as meter gauge, are also prevalent in certain parts of the world. The variation in track gauges often necessitates gauge conversion at international borders, where different systems meet. Trains either undergo a bogie exchange, where the wheel set assembly is replaced, or utilize variable gauge axles that can adjust to different track widths. This highlights the importance of considering gauge in international rail projects. Navigating bends, horizontal curves, and transition curves. Railway tracks rarely follow a perfectly straight path. Horizontal curves are essential for navigating geographical constraints and urban environments. These curves introduce a change in the track's direction, allowing trains to maneuver around obstacles and follow desired routes. Transition curves play a crucial role in ensuring smooth entry and exit from horizontal curves. They are gradual curves introduced between straight sections and circular curves. The purpose of a transition curve is to progressively increase or decrease the curvature. This gradual change minimizes passenger discomfort and reduces wear and tear on both the track and the train wheels. The radius of a horizontal curve is a critical factor influencing train speeds. A larger radius allows for higher speeds, as the curve is gentler. Conversely, smaller radii require trains to slow down significantly to safely navigate the bend. Engineers carefully consider factors like topography, train speed, and passenger comfort when designing horizontal curves and transition sections. Outsmarting centrifugal force, rail cant, and super elevation. When a train encounters a curve, centrifugal force pushes it outward, away from the center of the curve. To counteract this force and maintain stability, railway engineers employ a technique called rail cant, or super elevation. This involves raising the outer rail higher than the inner rail. Rail cant creates a slope across the track, effectively tilting the train inward towards the curve's center. This tilt counteracts the outward force of centrifugal force, enhancing stability and allowing trains to negotiate curves at higher speeds without derailing. The degree of cant required depends on the curve's radius and the intended train speed. Sharper curves and higher speeds necessitate a greater degree of cant to ensure passenger comfort and safety. Insufficient cant can lead to an uncomfortable ride and, in extreme cases, derailment. Speed limits and stability. How alignment affects different trains. Different train categories, such as passenger trains, freight trains, and high-speed trains, have varying operational requirements and speed limits. Track alignment plays a crucial role in accommodating these differences and ensuring safe and efficient operation for all train types. High-speed trains, for instance, require straighter alignments with gentle curves and minimal cant to maintain their high speeds. Freight trains, on the other hand, prioritize load capacity over speed and can tolerate tighter curves and steeper gradients. Passenger trains fall somewhere in between, requiring a balance of speed and comfort. Track alignment considerations for different train types extend beyond just curves and cant. Vertical alignment, including gradients and vertical curves, also plays a significant role. Freight trains, with their heavier loads, require gentler gradients to ascend and descend hills, while passenger trains can handle steeper slopes. Upward and onward, vertical curves and gradients. Vertical alignment focuses on the up and down movement of the railway track. It encompasses vertical curves and gradients that dictate the track's elevation changes. Vertical curves, like their horizontal counterparts, are used to transition smoothly between different gradients, ensuring a comfortable ride for passengers and reducing stress on the track and trains. Gradients, expressed as a percentage or ratio, represent the steepness of a slope. A 1% gradient, for example, indicates a rise or fall of 1 meter for every 100 meters traveled horizontally. Steeper gradients pose challenges for trains, especially heavy freight trains, as they require more power to ascend and increase the risk of brake failure during descent. Engineers carefully consider factors such as topography, train types, and operational requirements when designing vertical alignment. They aim to minimize steep gradients wherever possible, opting for gentler slopes to reduce energy consumption and enhance safety. Track alignment for safety and performance. Precise track alignment is crucial for safety and efficiency. It minimizes wear and tear, reducing maintenance costs. Proper alignment enhances safety by reducing derailments. It allows trains to operate at optimal speeds, ensuring a smooth and comfortable ride for passengers. Track alignment is essential for safe and efficient rail systems. International standards, a glimpse at global practices. To ensure a consistent and safe railway operation globally, various international organizations have established standards for track alignment. These standards cover aspects like track gauge, minimum curve radii, maximum gradients, and cant deficiency. While variations exist to accommodate regional differences and specific requirements, these standards provide a framework for engineers worldwide. For instance, the European Union Agency for Railways sets standards for interoperability within the European Union, promoting seamless cross-border rail transport. Similarly, the International Union of Railways develops and publishes technical standards and recommendations for railway infrastructure and operations globally. These international standards play a crucial role in harmonizing railway practices, facilitating the development of interoperable systems, and ensuring the safe and efficient movement of people and goods across borders. They represent a collaborative effort to enhance railway technology and promote the growth of rail transport as a sustainable and efficient mode of transportation. Conclusion: the enduring importance of track alignment. Railway track alignment, often overlooked, stands as a testament to engineering precision and its profound impact on our world. It underpins the efficiency of global trade and the connectivity of communities. Understanding track geometry unveils the hidden language of the rails. Embracing advancements in surveying and construction, the pursuit of optimal track alignment continues. It's driven by the need for safer, faster, and more sustainable transportation. Each track and curve embodies the importance of alignment in shaping rail travel's future. Appreciate the invisible forces at play, meticulous planning and engineering expertise. Track alignment guides us towards a future where rail travel remains a cornerstone of human connection and progress.